My name is Arpad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at COMSOL and how to set up elements for calculating displacements or forces and other properties of lumped mechanical systems. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. And after a short, brief introduction, we will look into what is a lumped mechanical system and what kind of elements are available in COMSOL Multiphysics. You can see some models through the demo session, and at the end you will see some summary of the properties of Multibody Dynamics Module. COMSOL is a multiphysics modeling, simulation and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. Once you have completed your COMSOL simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range application areas. These can all be combined with each other. We have modules for electrical, fluids, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And today's webinar and the functionality and the features will focus on the Multibody Dynamics Module, which is an extension to the Structure Mechanics Module. Multibody Dynamics Module is an expansion of the Structure Mechanics Module that provides an advanced set of tools for designing and optimizing multibody structure mechanics systems using finite element analysis. The model enables you to simulate mixed systems of flexible and rigid bodies, where each body may be subjected to large rotational or translational displacements. Such analyses help identify critical points in your multibody systems, thus enabling you to perform more detailed component-level structural analysis. The Multibody Dynamics module also gives you the freedom to analyze forces experienced by segments of the structure and stresses generated in flexible components that may lead to failure due to large deformation or fatigue. And here in this slide you can see a branch of the structure mechanics and the multibody dynamics interface. So we will use these lumped mechanical systems interface, which is similar to an electrical circuit interface. You may be familiar in the SPICE netlist. In the lumped mechanical system you can solve for scalar displacements and forces, so we will use and solve ordinary differential equations without dimension freedom, without a space dimension. There are several supported dimensions from 0D till the full 3D representation. There are several supported analysis types like a stationary or a parametric solver, or you can go for a full time-dependent solution. And you can connect to other modules, other capabilities to rigid or flexible bodies. And in the second demonstration example, we will see how you can do this in COMSOL Multiphysics. To do that, you can create subsystems like for a wheel or a seat. So you can couple lumped elements into one subsystem definition, and then you can create external sources. So you can couple your lumped mechanical system to other rigid domains. And here in a subset you can see that we have a multibody dynamics physics interface where a so-called applied force is set up, and that force comes from the lumped mechanical system interface. And under the applied force node you can enter the vector components to the desired set. There are lots of application areas where this can be used. These lumped mechanical systems can be expanded and used, like in automotive systems for a full vehicle simulation or simulating a subsystem, maybe a suspension system of a vehicle. It can be used in biomechanics for simulation of the human body. It can be used in civil structures, in MEMS devices, maybe in acoustics devices. If you want to substitute the diaphragm of a loudspeaker, this can be used with this lumped mechanical system interface. There are so-called two-port components like regular mass, spring or damper components. You can add impedance parts to your model, and there are the so-called external sources and displacement and force source that can be extended in your model. And there are single port components like a fixed node and a displacement node, but you can also add other nodes to your model. It can be a free node or a force node as well. So we will use some of these terminals in the upcoming demos. And as you've seen in previous slides, you can create subsystem definitions, so you can create your own definition, your own subsystem, and you can reuse it later in a bigger model, so you don't need to replicate it several times. You need to create it only once, and then you can reuse it whenever it is necessary. And also you can create a so-called subsystem instance, and it can be used to connect the subsystem model to other subsystem models or to the main system model. And our first example is a so-called quarter car model, where we will use the figure, the example that can be seen in the figure. So it's a simple 2-degree of freedom model, and we will use an eigenfrequency study and the frequency domain study to see the displacements and forces acceleration of this model. So we will use capital M car for the quarter mass of a car, and through a spring and a damper denoted with K2 and C2, it is connected to the lumped model of a wheel, which has a mass of capital M wheel, and in the subnode number 1 we will have a displacement excitation that will be used in the frequency domain study, and it's connected through a spring K1 and a damper C1 to the mass M wheel. So if we go to COMSOL Multiphysics, we can set up this by adding a 0D component, and from the physics node under the structure mechanics branch we can add the so-called lumped mechanical system to our component. And we can simply follow the node numbering like here in the slide. So spring 1 is between 1 and 2, and the same goes for damper 1, and between 3 and 4 we have the second spring and the second damper. Node 5, it should be a free node, and node 1 there is an excitation node, so we will add our parameter that's a displacement excitation. So if we set up these parameters in COMSOL Multiphysics, first we will disable the fixed nodes, since there are no nodes fixed in the model, but we have two masses. So we can start with the mass of the car, and if we go back here, so the mass of the car is between 4 and 5. So node names 4 and 5, put it 500 kilos. Okay, and we want to know the velocity and an acceleration, of course, in the results node. Go on with the spring, that's between 3 and 4. Okay, with the stiffness, it can be a parameter, but for simplicity we will use constant scalar values here. And we can set up the damper in the same way. This is in 3 and 4, like in the spring. And we can set up like this. Okay, we can add another mass, like a mass for the wheel. That's between 2 and 3, nodes 2 and 3. If we go back to our slide, so the wheel's mass is between number 2 and 3. Okay, let's put 30 kilos for that mass. We need the velocity and an acceleration as a result. And for the spring, that is between 1 and 2, and we have some values here. And we can set up the damper between nodes 1 and 2. Okay, so we have the mass of the car. That's a constant value. Wherever you can click in COMSOL, that can be a parameter, so it can be parameterized quite easily. We have spring 1, damper 1, mass 2, that's the mass of the wheel. We have a spring 2 and damper 2. Okay, and we need a free node since the car, the top, the node number 5, it moves freely in the y direction. So at number 5 we have a free node, and we need an excitation, a displacement node, which is applied at number 1. So it's applied at number 1, and put a parameter here, Ex. Parameters go here, Ex, let's put 2 millimeters here. So that will be our excitation. And then we can go to study. We can go for a frequency domain study node. Let's put a range of frequency values from 1 by 1 till 50 Hertz. And we can compute. Okay, and here are the default plots. The force amplitude as a function of the excitation frequency, the displacement amplitude as the function of the excitation frequency, and we have the same for the velocity amplitude for the two masses. So we have two curves, and we have the accelerations of the two masses as a function of the excitation frequency. And if you go on further, you can add, let's say, a parametric sweep, since we have a parameter value for the excitation amplitude. We can add this as a parametric sweep. So we can add like 2 millimeters, 4, and let's say 10 millimeters. So these will be the values for the excitation amplitude. So now we have 3 different solutions for the same frequency range. So we can recompute. Okay, and now as you can see, we have other solution values, and we can go back to the displacement field, and let's say we can go to the list value. So you can select the displacements of the bodies for the 2 millimeters, and you can plot other values for the 4 millimeter excitation nodes and for the 10 millimeter as well, or you can simple plot all of the solutions. And the second, more complicated example includes an 11 degree of freedom system, which means we have, as you can see, we have these nodes starting with number 1 till 12. So we have systems replacing the wheel. So we have a suspension system, and we have another system that represents the seats of the car. So we have 4 of these models at the top, so we have 4 of these seats. you can see in the blue circles, and under the rigid body we have the green circles. Those represent the suspension system. So we have 4 other degrees of freedom, and we have 3 other degrees of freedom as the rotations and the displacement of the rigid body. That is a simplified model of a car frame. So currently it's a rigid domain, so we have 11 degrees of freedom. And if we go back and open up this solved model in COMSOL Multiphysics, we can see how these subsystems and external modes are connected to a multibody dynamics interface. So here under component we have the lumped mechanical system. So we have a subsystem definition for the wheel with simple springs, masses and dampers. We have the same subsystem for the seat, 1 spring, 1 damper and a mass, as you can see here in the figure. So we have 1 simple spring damper mass model for the seat. And we have displacement nodes. We have 4 wheels, we have 4 different displacements. Those are functions of time, like this waveform. So these are the displacements at the 4 wheels. And we have these subsystem instances for the wheels. And as you can see, we have these so-called external sources where we can connect one and another node of this lumped mechanical system to a rigid domain. And that rigid domain is under multibody dynamics. We have 1 simple rigid domain, and we have 8 of those connection points. If we go back here, you can see that here. So we have 4 corners with 2 connection points, so we have 8 of those connections. And here you can see these applied forces at the different points of our rigid domain. 1 point is here, and if you go over, you can see all of these 8 points at the different 4 corners. And as you can see from the abbreviation, LMS means lumped mechanical system, and capital E3 stands for the third external source. So whatever force is calculated here at external source 3, this is connected to our rigid domain. So in this sense, you can couple a lumped system to a true multibody dynamics module, and you can calculate displacements and velocities, forces, whatever, in a car suspension system. So this is the time history of the angular velocity of the car, the centroid of the suspension of the car, and of course you can plot the displacements and accelerations at different locations, maybe at the seats, but you can select any other point where you want to plot and calculate forces or displacements. So with these external nodes you can couple lumped mechanical interfaces to multibody dynamics interfaces, whether it's a rigid domain or a flexible domain, and you can calculate forces, velocities, acceleration, whatever is in your field of interest. And at the end you can create a full animation where the body, the frame of the car is a rigid domain, and the suspension and the seats are modeled with the lumped mechanical system. So you can create a full vehicle simulation in this sense. So with the lumped elements you can create any modeling environment, you can create any system, whether it's a simple 2 degrees of freedom quarter car model or a more sophisticated with subsystem elements. You can have various terminal nodes, external nodes, free modes, displacement nodes, and you can easily couple to solid and or rigid domains with the so-called external terminals, so you can connect the force to a multibody dynamics module interface. And if you need more information on this module, that's a multibody dynamics module, which is an extension to the structure mechanics module. You can find out more at comsol.com. You will be given this presentation and the link to the models throughout the follow-up email, or you can connect us directly at our website or at our email addresses. So if you need a trial version, you would like to try out the software and the features and the capabilities yourself, just feel free to send us an email or contact us directly through our website. Now I thank you for your time and see you at our next webinar.